Uh, we can start our lecture now. So please go to chapter 4, maximum likelihood. So for this topic, I think you have learned a little bit maybe from other course about this maximum likelihood. Okay, so now for this section, it's quite easy the process. Okay, once you have formed the likelihood function, then the rest is no problem. That's only one that you need to take note how to form the likelihood function. Then after that, we try to maximize the likelihood function. So the objective of maximum likelihood actually is to find the parameters. Okay. So we estimate the best parameters under this likelihood function. Okay, so we were based on many conditions like individual data, group data. Maybe we have this truncation or maybe some others. Okay. Now we start now.
Chapter 4, Maximum Likelihood.
Section 4.1, Maximum Likelihood Estimation Complete Data.
In statistics, maximum likelihood estimation, or abbreviated as MLE, is a method of estimating the parameters of a statistical model with a given observation by maximizing the likelihood function. The method of maximum likelihood is used with a wide range of statistical analysis. For example, suppose that we are interested in the heights of adult female penguins, but are unable to measure the height of every penguin in a population due to cost or time constraints. Assuming that the heights are normally distributed with some unknown mean and variance, the mean and variance can be estimated with MLE while only knowing the heights of some sample of the overall population. MLE would accomplish that by taking the mean and variance as parameters and finding particular parametric values that make the observed results the most probable given the normal model. Firstly, we consider the individual data.
So for this section here, the example for the penguin, right? Which did I mention here? Just I heard, right? Yeah, yeah. The height. For example, let's say you have one group of this penguin. So your job is to try to measure the height. Okay, from this penguin. But too many, right? How you want to measure? It's impossible to measure one by one. Okay, due to cost or time constraint. Right? So we only take sample. Okay, we take sample from the and from there we try to measure the height. Assume the height is normally distributed. So under this sample from this penguin, okay, so we can do the MLE. Okay, we can do the ME for certain sample to determine the height of the population. Okay, so that is this is one of the example for this MLE. Okay, so let's carry on to next.
Of the overall, we would accomplish that mean and finding particular parametric normal model. Firstly, we consider the individual data. Maximum likelihood is a relatively simple method of constructing an estimator for an unknown parameter data in a parametric model. In order to define the maximum likelihood estimator, we start with the following notation. Let the data set be a group into events A1, A2 until AN, where AI is whatever observed for the ith observation. The event AI can be a single point, that is single individual data, or an interval, that is group or censored data. Furthermore, the event AI results from observing the random variable xi. We assume that the random variables x1, x2 until xn are independent and their distributions depends on the same parameter that need to be estimated. The method of maximum likelihood is to estimate the parameter that maximizes the probability or the likelihood of getting the data we observe. This is done by maximizing the likelihood function as follows. That is, this likelihood function L data is defined as the product of the probabilities of the random variable xi, which belongs to the event AI, when the distribution depends on the parameter data. We use this notation to indicate that the distribution depends on a parameter data, where this parameter data could be a real value unknown parameter or a vector of parameters. In the case of complete individual data, consider a random sample with observed values x1, x2, x3 until xn, where xi has ni observation. Then the likelihood function is given by this, where this function f is a joint density if the xi's are continuous, or a joint mass function if the xi are discrete. So this joint density function is equal to the product of the PDF if x is continuous, or maybe it's a product of the PMF if the x is discrete.
Okay, so as I said, this likelihood you must understand how to form. Okay, so if this is this section is for individual. Now we move to the data when there's individual data. So when you want to form the likelihood function, that you have to consider the product. Okay, multiply all the PDF. Okay, if this x is a continuous, you multiply all the PDF. Okay, if the x this random variable is discrete, then you multiply all the PMF. Okay, so this is the definition. Okay, that is here. Okay, so based on the individual data, you have to know A is an event. Okay, x is a random variable. Okay, if this random variable belongs to this event A, so you need to multiply all the PDF or maybe all the PMF, but depends on this random variable is continuous or discrete. Okay, I will show example later how we want to form.
X is discrete. Estimate of MLE is the value of data that maximizes the likelihood function, that is L data, by applying the optimization method from calculus. To maximize the likelihood function, we may proceed to log likelihood function, that is, we apply the natural logarithm in likelihood function. That is, we define as a small letter L of data.
Okay, now after you form the likelihood function, you may proceed to log likelihood. That is, you take the log, okay, at this likelihood. But it's not necessary. Okay, please do not mistaken. Okay, you have to look at the likelihood function. Most probably we apply the log. Okay, but certain function no need. When you apply, it's much more complex. Okay, so in calculus, you know why we want to apply log, right? Because easy to differentiate, okay, for certain function. In this topic, chapter 4 here, most of the likelihood function we should take, or most, not all, most of the functions should take. Okay. In my tutorial question, maybe I have one or two that is no need to take, but you still get the same answer, do not worry. Okay, that you learn from calculus, right? Either you take log or you didn't take log, you differentiate it, you maximize, you take second order, you can test it, you can see the answer will be the same. So next we go to example 1.
Example 1. Consider the following discrete random variable x whose PMF is given below. So we have the data from this random variable x, which is 0, 1, 2, 3. So this is our x1, x2, x3, and x4. And this is the PMF in terms of the parameter data, where the data is in between 0 and 1. And the number of observations of the data is given here. Consider the following random sample of 7 observations taken from this distribution. Determine the likelihood function. So this is equals to the product of the PMF. That is, we try to take all this PMF from the first data and to the power of 1 until the PMF from this data to the power of 2. So this problem solved. And next, we have to find the maximum likelihood estimate of data. That is, from this likelihood function, we have to take the log likelihood. That is, by taking the log at this likelihood function. And next, we have to differentiate to the first order and also the second order. When the slope equal to 0, then we can find the data and we test in this second order so that this is always negative. Then this problem solved. Solution for example 1. Part 1. Given the discrete random variable x, where observations are as follows. That is, x1 equal to 0, x2 is 1, x3 is 2, and x4 is 3. Corresponding to the frequency n1 is 1, and n2, n3, n4, they are equal to 2. Then the likelihood function is given by this. Since this is a discrete, that is, we try to multiply all the PMF for the corresponding x value and based on the frequency respectively. So this is equals to the probability when x equal to 0 to the power of 1 and multiply the probability when x equals to 1 to the power of 2 and multiply the probability when x equals to 2 to the power of 2 and multiply the probability when x equals to 3 to the power of 2 as well. And we have to substitute all the PMF values from here. So 0 will give this, 1 will give this, and so on. So we will have data over 3 power to 1, and this will give 1 minus data divided by 3 to the power of 2, and this will give me 2 data divided by 3 to the power of 2, and this will give 2 times 1 data divided by 3 to the power of 2. So we simplify this, we will have 16 data cubed multiply 1 minus data to the power of 4 and divided by 2187. Part 2. The log likelihood function, that is small letter l in terms of data, which is equals to the log of this value, that is 16 theta cubed 1 minus theta to the power of 4 divided by 2187. So simplify this, we will have log 16 divided by 2187 plus 3 log theta plus 4 log 1 minus theta. So we differentiate respect to theta, this becomes 0, and this is 3 over theta and plus 4 over 1 minus theta, and this coefficient of theta, which is negative, and simplified we will have 3 over theta and minus 4 divided by 1 minus theta. Now if the slope equal to 0, then this is equal to 0. So if you solve this equation, we will have theta, which is 3 over 7. Now let's go to the second order of this log likelihood equation. We will have negative 3 over theta square, and this will give me minus 4 divided by 1 minus theta square. Now, since the second order, when theta is 3 over 7, you can substitute the theta as 3 over 7, then you will have this result, which is negative. So therefore, we found the estimate of this theta, which is 3 over 7 under this MLE.
Okay, here I want to highlight for this problem part A, of course, you know how to find the likelihood. Okay, just multiply all the PMF because this is a discrete event. So for part 2 here, the question has to find the maximum likelihood estimate of data. So you, other than this, you take log both sides. So if you just imagine, if you don't take log, you also can differentiate this by using the product rule, right? UV. You also can do that, no problem. Okay. But if you take the log, that is much more easy to be calculated, to be differentiated. Okay. So just imagine if you take UV, you need to factorize later. Then I think you may have problem. Okay, but you can do with that method. No worry. I can. Okay. So if you take log, you can see that after you simplify the logarithm, they take differentiation, then much more easy, right? If you differentiate that only this, right? So it's so simple. Now, once you have a first order, you quickly go to the slope equal to 0. That I want to know what is the value of the data. Okay. After that, you use this data. You must go to the second order. Okay. Although you may know that this is already confirmed is negative, but you still your working you still have to show it is negative. Okay. Once you have a second order, you substitute the value you found. That you have to prove that the second order is always negative with the data value. Then only we can confirm that this under MLE, the estimate of data is 3 over 7. If you reach this step, okay, you go to first order. When the first order equal to 0, you get the answer, and you conclude this is the estimate. You won't get the full marks because you didn't test it. Okay, MLE, you have to test it. This is a maximum under MLE. Okay, it's quite simple. Any questions? So we may go to next slide. So now we go to example 2.
Example 2. A random sample of 5 claims obtained from an exponential distribution with parameter data is given as follows. That is 15, 10, 7, 8, and 20. Find the maximum likelihood estimate of data. So we let our x be the claim random variable, that x is exponentially distributed with the parameter of data. So by considering this observation here, we have to estimate this parameter data by taking the maximum likelihood estimation. So we have to form what is your likelihood function. Since this exponential is continuous, that means we have to multiply all the PDF from these 5 observations. And next, we have to get what is a log likelihood function. And we differentiate in the first order and next to the second order. So when the slope is equal to 0, we have to test the data whether is negative. Then this problem solved. Solution for example 2. Let x be the claim random variable such that x is exponentially distributed with the parameter data where the PDF is given by this. And this you can get from table C. Now given the 5 observations, which is 15, 10, 7, 8, and 20, then the likelihood function is given by the following. So we have to substitute all the observation inside this PDF, and we will have the likelihood functions as follows. So the first PDF, when we substitute the x is 15, and multiply the second PDF when we substitute the 10 inside here, and so on until the 5th observation 20 substitute into the PDF. We have this PDF. Next, we try to simplify. We will have 1 over data to the power of 5, and sum up all these indices, we will have negative 60 over data. Therefore, the log likelihood function, which is equals to log 1 divided by data to the power of 5, and multiply this exponential to the power of 60 over data. So simplified, we will have, this will give me negative 60 over data and minus 5 times log data. And next, I try to differentiate respect to data. So I will have 60 over data square and minus 5 over data. And the second order, this will give me negative 120 divided by data cube and plus 5 over data square. Now, if the slope is equal to 0, then this equation is equal to 0 as well. This can be simplified as a quadratic, and it can be factorized as follows. Now, since data cannot be 0, therefore data must be 12. And next we try to test this data value in the second order. So since the second order, when data is 12, so we can get this value, which is negative. So therefore, the estimate of this data, which is 12 under MLE.
Okay, quite obvious. I believe you know how to form the likelihood. Just multiply all the PMF from this observation. Under exponential, that you can get this PDF from the table C. So you just multiply, okay, multiply all the PDF, okay, and then simplify this, right? So next, if you don't take log at book, if you don't take log, you can differentiate by using the quotient rule. That's U over V. Okay, if you can do, you go ahead. But I think your working become longer or maybe more complex. Okay, because you need to differentiate later. Okay, so if you take log, you can see that the next step you differentiate is very easy, right? From here, you just differentiate just one line only. Okay, and of course you have to take the second order. And next, of course, when your first order equal to 0. Now here I want to highlight a class. Some student they go and cancel off the data. You must give reason, okay? Because you cannot simply delete off the root. Data is the root, okay? Once you want to delete, you must give reason, okay? The reason is because your data is not 0, okay? Your data is not 0, therefore okay. So do not cancel off data here without reason and give me answer the data is 12. I will cut your marks, okay? Or in other words, you won't get the full marks in your working. And of course, next you know what to do. That is, we can test in the second order. Then only you can make conclusion. The estimate of data is 12 under MLE. Okay. So any questions? Then we move to next. That is the group data. So we have done the individual data. So how to form the likelihood function under individual data, and now we move to group data. So for group data, we have another method to form the likelihood function. Okay, let's see how is it. Okay, so this is maximum likelihood for complete data. So complete data for individual and group data. Later we have incomplete data. Okay, so we have done individual, now we go to group.
Group data. For a complete and group data, the process of finding the maximum likelihood estimate is as follows. Arrange the unique observation values in increasing order, that is this, where C0 is the smallest possible observation, often 0, and Ck is the largest possible observation, often infinity. We let Ni be the number of observations in this group, where I is from 1 until k. Then the likelihood contribution of each value in the ith observation is given by this. That is the probability of random variable x in the event of AI, which is equals to the probability of x, which lies on the interval from Ci minus 1 to Ci. And this can be simplified as the CDF at Ci minus the CDF at Ci minus 1. And this can be explained by the line diagram. Consider interval from Ci minus 1 to Ci. So the probability in between this interval, that is, we try to find this CDF minus this CDF, that is this, or this probability can be explained by survival, that is, we try to take this survival at Ci minus 1 minus the survival at Ci, and which is depends on the parameter data. So from each of the factors, then we can find the likelihood function as follows. That is the product of the each factors from each group. Proof. Since the likelihood function is given by this, therefore, this likelihood functions, which is equals to the factor.
Okay, class, this proof actually is for this section. I think I didn't mention that the likelihood is in terms of the product multiply this probability. If you simplify this, it will become the summation. Okay, summation or log of this probability in terms of CDF. Okay, so I'm going to prove this. How we change the summation to the product to become the summation. Okay.
Proof. Since the likelihood function is given by this, therefore, this likelihood functions, which is equals to the factor for the CDF at C1 given theta and minus the CDF at C0 given theta to the power of n1, and multiply the second factor, that is the CDF at C2 given theta, and minus the CDF at C1 given theta to the power of n2, and multiply the last factor, that is the CDF at CK given theta, and minus the CDF at CK minus 1 given theta to the power of NK. So we take log for both sides, then we will have the log likelihood function, which is equals to N1 multiply log of this first factor plus N2 times this log for the second factor and plus until Nk multiply the last factor. So this is a summation for the Ni and multiply log of the factors when the CDF at Ci given theta minus the CDF at Ci minus 1 given theta, where I takes from 1 to k. So we have proved the result.
Clear? So to prove this product of this probability in terms of CDF, right? You just multiply all this CDF with the corresponding power to the corresponding of this frequency. So if you take log later, so you can see you sum up become this in terms of summation. Okay, the proof is quite easy. So actually, we no need to memorize the formula because once you have this likelihood function, you just take the log, you just simplify. You are doing this process. Okay, no need to memorize this formula or this formula. The concept is important. The concept will lead you to take log or without take log. Okay, so this is the concept how we want to form the likelihood function from the group data. Okay, under complete data. Okay, so you move to next example 3. So example 3, you can see this question is involved the group data. Okay, so we try to form the likelihood function, and then after that we try to estimate the data. Okay, so here we go.
Example 3. Suppose that a group of 20 losses resulted in the following chart. That is the loss given in terms of group with the corresponding number of observations. Suppose losses follow the distribution which is given by this CDF, where X is strictly greater than the parameter data. Calculate the maximum likelihood estimate of data. So we have to form what is a likelihood functions by using this formula, and next we try to find the log likelihood functions. So from the log likelihood function we have found, then we need to differentiate for the first order and also the second order. So when the slope equal to 0, we can find what is this data value, and we test it in the second order. So if this is less than 0, that means we solve the problem. Solution for example 3. Let X be the loss random variable such that the CDF is given by this, where X is strictly greater than data. Then the likelihood function is given by this. So we try to substitute all the boundary values to the corresponding factors. That is, the first factor we have the CDF at n minus the CDF at the least value, that is data, and to the power of 9. So please take note, the least value for the first group, we shouldn't take 0. That is because if the data is divided by 0, X is really greater than data, then data is the least value in this group.
Okay, this is very important, class. Okay, so do not see